buttons there. I want to turn this other light on. A little better, right? Okay. Good news and bad news. Easiest section to theoretically cover. Static equilibrium just means the sum of forces on an object equals 0 and the sum of torques on an object equals 0. Done. That's the whole chapter. In theory, you know how to do forces already. You know how to do torques already. Ha! Right? In practice, this section, this is the downside now, has the most like tricks and shortcuts and tips. And it's kind of like chemistry in the sense of chemistry, there's a lot of exceptions or a lot of rules you kind of want to follow. And so you really only get good at this section by doing a lot of problems and getting some experience and be like, oh, when he does this, usually there's this trick that helps. Now, I'm going to try and teach this section in a way that makes them all as similar as possible so that you don't have to know as many tricks. And when I teach you a trick, I'm going to try and clarify, you could use this trick or you could do it this way. So maybe that's not the smartest way, but it's the way I feel like teaching it. So I apologize if at times it feels like you're drinking from the fire hose. Good news is I think we got 2 days for this and we're done. So some general tips. Usually more figures are better. So I'm just going to say draw lots of pictures, big pictures. It turns out we need to label stuff. And these pictures, if you get in the habit of drawing like a quarter of a page rather than a tiny, tiny picture, that's going to help out. But you may even want to use a whole sheet of scratch paper for your picture on the test, right? That way you could draw it and label it and actually read what you wrote on it. It gets really tough. Okay, so draw lots of pictures. In particular, in my opinion, this is a recipe for success. Separate pictures for lengths and angles and FBDs. So obviously your free body diagram, you don't want to be labeling a lot of lengths and angles on there because it gets confusing. There's going to be times where we do that. We're going to try to avoid it. And what I'm saying here is basically one picture for your FBD, a different picture for figuring out lengths and angles, all right? I'm going to say this one. Try to be consistent in how you approach the problems. Now, this is subtle. What I mean by this is you want to attack these problems and do them all in the same order, in the same way. Whatever way you choose, there's lots of correct ways. I'm going to show you one method. For example, I like to do torques first, then I write forces. Somebody else, I was talking to an engineering instructor, they like to use forces first, then do torques. But the idea is I like to do them all the same way. And for example, remember earlier in the semester we said sometimes you could say the ups equal the downs for forces. Do you remember that? What I mean is when I'm consistent, always write the ups on the left side of the equal. Always write the downs on the left. And then you could say the rights equal the lefts. And again, this is only valid if acceleration is 0, which is true for static equilibrium. And so little things like always trying to write things in the same order helps you reduce little mistakes. Does that make any sense at all? Okay, it's sort of like when I color-coded things, I always drew the acceleration in red so that I knew when I looked at something in red, it was the acceleration in chapter 5. All right. Anything else I want to say? I guess said another way here, we're saying A equals 0 and alpha equals 0. That's another thing that we're saying here. Do you agree? If the force, net force is equal to 0, translational acceleration is 0. If the net torque is 0, angular acceleration is 0. A subtlety that sometimes gets lost is this is true. Okay, it turns out if there's no net force, it's not accelerating. If there's no net torque, it's not rotating about the right end, the left end, the top end, the bottom end, the middle. It's not rotating about any spot. And this can be very useful. In fact, what it allows us to do is, in the previous problems, we would do sum of torques about the obvious pivot point in a problem. Now we could choose any point because every single point has no rotation. Subtlety. Should we start doing a real problem and see how this works out in the real world? Now, this is too much to understand right now, this page 99. So why don't we do a couple of problems and come back and read it at the end of class today and see if it's starting to make some sense. Cool? So, all right. I'm going to start with 12.1. And just to give you a feel for it, I'm right behind you two. So I'm just going to point this out. I'm right here. You guys can kind of get out of the way. All right, so I've got two scales here, right? I don't know if you can see these on the Zoom, but I'll zoom it in. And the idea is I can just lay down on this board and we can get my center mass. My claim is if we get the scale readings under each end of the board, and notice the scales right now are 0, aren't they? Pretty much. Right? So the idea is that's going to negate, we don't have to worry about the weight of the plank itself. So let's go up to the board and draw this out before we do the weight. Okay. Thanks. Sorry I made you run around. We're going to be doing a bunch of demos over there. Oh, you figured it out. Okay. All right. I think I called this 12.1, didn't I? Okay. So the mass of the plank, we're going to ignore. We're going to call that 0. I'm able to do that because I zeroed out the scales with the plank on there. It actually has like 10 pounds of mass, but compared to me, unfortunately, 10 pounds is negligible. Right? So there's a scale here. There's a scale here. And then there's a person laying down there. This is me. My nose, my head. Okay. So that's supposed to be me. In this case, I'm going to put some shading in here just so you can see a little bit better. Okay. Now, I have some center mass. Presumably, it's right here, this large baby that looks like my belly here. I'm going to call it right there as my center mass. There's an mg from my body going down this way. And then in this case, I want to label some distances here. I think, what's the entire length of the board? Did I say it was L or did I say it was D? L. Okay, so the entire length of the board is L. We could measure it with a meter stick. I believe in practice it was 187. There we go. This distance is going to be what we're trying to figure out. X, the distance from my feet to my center of mass, and then we're going to get some scales. There's going to be a reading on this scale. I believe I call this one NA. I just call this point A for no good reason. This point B. So I'm just calling the left end A and the right end B. Now, what I actually want to do, this is just my figure to get a feeling for it. You see, I've got a lot of dimensions and lengths on here. This is not going to help me solve the problem, or if it might in this simple case, but I want to draw a separate FBD now of the beam itself. So here's the beam. We're letting the mass of the plank or the beam or whatever you want to call it, the mass of the piece of wood is 0. What is one force acting on it? The two normal forces. What do you think? Are they exactly the same in size, or is it possible that one end of the beam might be having to support more of my weight than the other? What do you think? Is it possible they're exactly the same? Is it possible they're different? What do you think? Let's say I stood at this end. Wouldn't this end have to support almost all of my weight? And so it's possible they're not exactly the same. Do you agree? And that's all I wanted to point out. What type of force do I exert on the beam when I lay down on it? Yes, I heard mg. That is correct in this special case, but I want to go into that a little bit more in depth. Do you agree I really exert a normal force on the board? But because it's not accelerating, do you agree that normal force that I exert on the board should be exactly the same as my weight? Are you okay with that? In this chapter, we're going to use that all the time. It's not valid in chapter 10, right? Remember, the tension is not mg all the time. But okay, anyways, so I'm going to label this one as, even though I exert a normal force down, I can say the normal force that Rob exerts on board. But it's a lot easier to just write mg. Do you agree? And since that happens to be true, that's what we're going to do. It's not true all of the time. Only in chapter 12. Only in chapter 12. Okay. Now, there's point A over here. There's point B over here. Let's label those, point A and point B. What I'd like to do next is to write down the sum of torques about a point. Now, I can choose wherever I want. It's not rotating about A, it's not rotating about B, it's not rotating about this point. Those are the three obvious points to choose. I can do sum of torques about this one, and that will eliminate this force. Now, think about this. If I choose A as my pivot, you're free to choose whichever one you want. Why does the force NA not cause a torque? Line of action through the pivot. That means this one will be unimportant, okay? And so I get two terms in my equation. I could solve for something. Okay, so let's keep going here. Now what I want to do is I want to do sum of torques about point A equals 0. I want you to be systematic when you do this. So this is how I approach it. I start at the pivot point and just start working my way across. NA, no torque. There's going to be a torque due to Rob's normal force, and then there's going to be a torque due to NB. So I'm going to write them in that order. Torque due to Rob plus the torque due to point B or whatever. So there's two torques. They're going to add up to 0. Notice there's a vector on these. Is this pace about right? Too fast, too slow, about right? Most of you? Good? Okay. Now, in this case, what we used to do in forces, we'd always draw a coordinate system. Now what I'm going to do is I'm going to say, I'm going to arbitrarily choose this way to be a positive torque and this way to be a negative torque. This is the standard math convention, right? Things that rotate this way are considered positive, that way negative, sort of like in the computer code. And rather than saying plus or minus k hat all the time, I'm just going to put in plus or minus signs here. We're going to imply a unit vector, just like we did with kinematics. So let's do this. The torque due to Rob's normal force, is that going to be positive or negative according to this coordinate system? Negative. What's the equation for the force? Or for the torque, excuse me. You remember any equations for torque? What was it? Oh, yeah, true. It's I alpha, except what's alpha in this problem? 0, so that's not going to help. I was thinking of the one that's like torque equals R cross F, but usually we wrote that as RF sine theta or R perpendicular F. Do you remember that? Or sometimes we even wrote it as RF perpendicular. Am I still on, Alan?
Yeah.
Just barely?
Yeah, sure, yeah.
Do you remember that now when I say it? Does that make more sense? Yeah. It's like all those different ways, and then we'd get the direction with the right-hand rule. Rather than doing the full cross product, I think we'd be insane to try and write this. You could do it and it would work out. Trust me, it would be great, but I think it's easier to just use this one. If you had to pick one of these methods to get, this RF sine theta works pretty well for this class. It's not going to work well in a 3D class. This one works for everything. This is probably the next most general. But for most of what we do, this one's excellent. Okay. Let's do it. I need R. What does R mean? Do you remember? It was from what to what?
From the pivot to the force.
So from the pivot to the point where force is applied, let's do it. What's the distance from the pivot to the point where my normal force is exerted? Hint, we drew a separate picture with our lengths in it so it wouldn't be so crowded. What's the distance from the pivot to this mg? We called it x, right? Next, the force. I got that one, mg. Now here, I should be careful. Instead of saying theta all the time, students tend to screw up and just shove in theta. I'm going to say angle, okay? Because sometimes it's theta, sometimes it's 90, sometimes it's 0, sometimes it's 180. It's different in every problem. So in this case, I'm going from the pivot to mg. So this is the r vector for mg. What does the angle look like between the r vector and the force? What does the angle look like between the r vector and the applied force mg? Got it? And notice we already took account of the minus sign from the coordinates. R goes to mg into the page. In this case, we call that negative. Again, I'm going to show you that. from the pivot to the force, R cross F, curl your fingers to the force, thumb points into the page, we've called that negative for this problem. Is that good? Okay, next. The torque at point B, how far is it? L, we call that L. Is it positive or negative torque? Let me do this in a different color. Sorry. See what I mean about, this is like the easiest problem. It's already way too busy. This is R for normal force B, agreed? What's the angle between look like? Another 90. We get L and B. Does anybody know what sine of 90 is really quick? That's 1. So I'm going to rewrite this. And just to simplify my life a little bit, I might just say XMG equals L and B. Take a second to make sure you believe that that's legal. Basically, I move this to the other side and then flip the sides. Good at that? Move this over and then flip the sides. That's our equation from the sum of torques. Maybe I'll label that. So now I know where that came from. That was from sum of torques about point A. Cool. Now I want to do sum of forces. I want to do sum of forces in the X equals 0. And sum of forces in the Y equals 0. I promise to get out of the way here. Okay. Oh, shit. Huh. What are the forces in the X direction for this problem? Nothing. Do you agree we don't even need to do sum of forces in the X direction? Sorry, I wasn't even paying attention. I just got in the habit of always writing that. So in this case, there's no reason to. That gives me a little bit more whiteboard space, which I need. Well, give me one force in the Y direction. And A, another one. What's that? And B. Do you agree that's the ups equal the downs? Is everybody okay with ups equal the downs here? All right. Now, at this point, what are the easy things to get from this experiment that we saw over there? In particular, take a look at that experiment. What's going to be the easy things for us to obtain in the real world with this experiment? Okay. Yeah. Oh, good. You're already there. Sorry, I'm too busy trying to figure out this crap. All right, my bad. Look, we have scales, so we're going to read these two things. Obviously, we can add them together to get my total weight, but it's easier to just figure out the center mass. So what I'm going to do is plug this into here. I just want to point out that X is equal to the length of the board times NB over NB plus NA. Again, I just took this mg is this, plugged it in, and shifted it over. We can use this to find the center of my mass. Got it? Like I said, I measured this board earlier this morning. It's 187 centimeters. Let's just go do it. So then I'm gonna, yeah. Whoops. Sorry about that, Alan. Getting right in here. Oh my gosh, come on. There we go. I think if I get this close enough, you'll even be able to see the scales in the picture. Can you move that chair, Alan? Yeah, thanks. Just maybe roll it the hell out of there. I think. I'll spare you guys pain of having to wait yourself in front of the class. Is that on now?
Yeah.
All right, so hopefully they're all at 0. All right. So punch these numbers in after you get this. Slow. Laying down on the job. I'll get this in class. All right, what do we got? Oh, wait, I should probably put my hands down. That's not going to do this. Okay. Got it? You got the scales, somebody? Can you read those down?
Do you want the decimal points?
Yeah, sure, whatever.
103.4 on the left.
By my feet.
Yeah.
Okay,
And then 140.9 like I said.
got it?
Okay.
Totally didn't hear all that, but I think, let's get it, let me write it up here. That's right, 250 pounds of fury right here. Okay, so what did you say it was? And the left one here, NA was 109, you said?
103.2.
103.2 pound, not LBS, whatever. NB, that was the 149. Is that right?
140.9.
140.9. Oh, I lost weight today. All right. So in this case, let's punch them in and see what number you get. And remember, L was 187. I'm gonna get my calculator up too. Okay. 187 centimeters times 140.9 divided by what'd you get? Basically 108. Is that what you got? Anybody else? All right. So for reference, we can see where that is. That's a meter stick. Then we got to go up, what, another 8? Oh, yeah, right there. Whoa, whoa. All right. Looks about right. That's what beer does to you. Okay, there's one last thing I want to do with this problem. Any questions so far? Good? Okay. For extra practice, I want to prove that I'm not lying to you. I want to do the sum of torques about point B. All right, and I'm going to redraw this one because I don't want to screw it up. Which force is going to drop out if I do the torques about point B? Which force is going to drop out in the torques? NB. This one should not matter. Now let's go across. There's going to be an mg. Technically, it's the normal force I exert. Okay, and then there's NA. Anytime we do this, we should probably draw a coordinate system. Now check this out. I'm going to choose to call this way positive. It doesn't frickin' matter. Do you agree? And I'll call this way a negative torque. That's actually the same coordinate system we used flipped all the way around. Standard math way is positive, right? Why not? So now there's going to be a little more space here. There. Hopefully you can still see that online. In this case, I want to do the torque due to mg plus the torque due to NA equals 0. Okay? Do you agree there's no torque due to NB? Help me. What should I write for the torque due to mg? What's the distance?
L minus that.
L minus x this time. This distance was x. This distance was L. Now we got to be careful. That's L minus x. Okay? I hope that makes sense why. So I'm going to have an L minus x. The force is mg. The angle is 90 degrees. So sine of 90 is 1. According to this coordinate, should mg be causing a positive or negative torque in this picture? In this picture. Start at the pivot. Walk over to it. Curl your fingers in the direction of the force. Is that a positive or a negative according to my chosen coordinate system for this part?
Positive.
Positive. Good with that? And then, do you agree the other one's going to be negative? Am I still on, Alan?
Yeah.
Good. Now, out of all this, at first, you might say, well, this looks totally different. But I want to point out, where was that? Where was that? Look, if we put this into here, watch what happens. We're going to get a L minus X times NA plus NB, that's from the force equation, equals L NA. Well, when you factor this out, I get an L NA plus L NB minus X, and I'm going to get lazy here, NA plus NB. Still on, Alan, or not?
Yeah, he's still on.
Okay. And notice in this case, this drops out. This moves to the other side, you get back this answer. Do you see it? I was just trying to show you that we could have chosen any point you wanted. That was it. Trying to prove to you, at least with one case, that the chosen point for torques doesn't matter at all. You could choose something different than your friend and we all get the same answers. Is that enough on that? All right, let's take it up a level here. Maybe I will get up the next. Probably seen this hanging around, wondering what the hell we were going to use this thing for. Whoops, I think we want it this way. I'm looking at problem 12.2 at the top of page 101. I'm going to erase the board. Will you read the problem really quick? So give me a second. Is the pace okay, or am I going too fast? What do you think? We good enough? Okay. I just have no idea what works for you guys, right? So you're actually getting quite fast. So I'm trying not to bore you. Funny, we had a pretty rough start to the semester. But I gotta say, I mean, now, I wish maybe more people would have survived the class, but I gotta say, whoever's left, man, it's really nice working with you. You guys are great. So I appreciate all the hard work you're putting in. It's obvious that you're working. All right, let's look at this stupid thing. Whoops. Whoops. Okay. So I've got a beam, we've got a cable, we've got this hanging mass here. Oops. Hopefully you can see it over on that side too. There you go. So let's just kind of brainstorm before we attack this one. I think it's all on there. What's one force that's acting on, the beam itself? Let's make this beam what we care about, this piece of wood. What's one force that's acting on that beam? Mg. Mg of what? Okay, of the weight. Excellent. Technically, there's a normal force between the hook and here. But do you agree that in this special case, the normal force actually equals mg for that interaction right there? Absolutely, and that was one of the questions. You just answered question B. Actually, it's a normal force, but really we're going to call it an mg because of what you just said. Are you cool with that? Everybody else? All right. What's another force acting on this beam? Mg of the rod itself, agreed? In this one, we can't just ignore the mass of the beam. It's not negligible anymore. For reference, the beam is 200 grams and this is 1,000 grams. So this is a lot more, but not, this is not negligible. What else? Tension in the cable, right? Feeling good on that? Any other forces or are you good? The pivot itself, there's a hinge right here, right? This hinge, what way do you think the hinge is exerting force? It's got to have some component up. Do you agree? Otherwise, this thing would fall down here. Do you think there's any component left, right, side to side? That's the hinge. What's this string? Which way is the string exerting a force on the rod? Is there a horizontal component from the string force? Yeah. So what does the pivot have to do to keep this rod from falling off? Has to exert a force this way, agreed? In general, the trick is anytime you draw a pivot, just assume there's an X and a Y and draw it. If one of them turns out to be 0, cool. Got it? Okay, so let's try and draw this thing up. 12.2. There it is. 12.2. So I'm going to try and draw a picture of this thing. There's a wall here. There's a pivot. There's the rod itself. There's a cable. Put some shading in just so I can see it a little bit better. This is the standard symbol for a pivot, this kind of half circle with a hole in it. That's the standard symbol for a pivot. You'll learn much more about that in the statics class if you take one. And then I like to do all of my dimensions on here. Now I happen to have some dimensions here in these. Okay, so the length of the rod, let's just call that L. It's 56 centimeters. This height in this picture here, I've got it recorded, is 42 centimeters. Earlier today in class, when I was live streaming this, I wrote down the wrong number here, and we got a bad calculation. I didn't know why. All right. I think in this problem, they label this angle as theta, right? Is that right? Yep. Then there's some extra mass sitting on here. And notice we're going from the pivot to the center of mass. And so, to clarify, mass of the rod is M, is 200 grams. You know what? Why don't we shift this to kilograms? Is everybody okay with that right now? So we don't have to think about that later. 200 grams is 0.200 kilograms. And then mass of the point mass is 5m equals 1.000 kilograms. Okay, it's approximately true. And I think, what did I call this? X in the picture? X is a variable because we can change the location of this wherever we want it, okay? So for right now, we're gonna leave this as X. At the end, we could choose X equals L over 4 or X equals the full length and just see how the tension varies. All right, by leaving it X, it gives us some flexibility. Okay. Now, let's do an FBD. That picture is for understanding the dimensions and such. Peter, you said a force. What was it?
MG.
Mg. And that was for the point mass or the rod? Point mass, I think? Or both, they're both there, right? And they're not necessarily at the same spot. Do you agree? So we've got mg and we've got 5mg. That is not really in the middle of the rod, is it? Supposed to be. Should be over a little bit, sorry. I think that's a little better. Sorry about that. You should try and draw these pictures fairly well. A well-drawn picture can help you avoid mistakes. What was another force? Ryan, you had one? Tension in the cable. Whoops. Tension in the cable. I'm going to make that a little shorter. Sorry. I'm just running out of room. Not to scale. Sorry. I'm doing the best I can here. What other forces? The pivot. And so I'm going to label that. Maybe we don't know which way they point. So what I'm going to do is I'm just going to default and always assume Rx is to the right and Ry is up. Unless I have a good reason to suspect otherwise, I'm just going to assume this. And you might be saying, what happens if you choose wrong? If you choose wrong, just like chapter 9, at the end of the problem, you'll get a minus sign. The correct answer is opposite the direction you chose to draw. I'll discuss this in the summary later. For now, just when you got a pivot, just draw Rx and Ry to the right and to the left in the standard X direction and the standard Y direction, and just do that all the time so you don't screw this up. I'm going to go one step further with this FBD. I want to draw the tension with components. In particular, I know this angle down here is theta. Now, just give me your attention for a minute and watch, okay? I don't want you to screw this up, so just watch this for a second. We used to always go like this, right and up. What I want you to do now is put all of the tails in the same spot. And I'll show you what I mean. That is T cosine of theta, agreed? And this, so rather than having them be here and here, I want all the tails in the same spot. Did that make any sense? I just took this side and then moved it over to here. So I'm doing the same components, right? This is adjacent, so it gets T cosine. This side would be T sine, and then I just move it so its tail is in the correct spot. That's crucial in this chapter because the torque depends on where the force is applied. If you draw it over here, that's not the correct location for that force component. I don't know if that made any sense, but good enough? Okay. I want to do some torques. If I wanted to learn something about this problem, I know the masses and I know the lengths. What are the unknowns in this problem? What are the unknowns here? T, Ry, and Rx. You might be saying, well, what about theta? Do you agree we could figure out theta from these dimensions? So in theory, we could get theta. More on that in a minute. So in real life, usually you know the masses and the lengths of something, and you're trying to figure out the size of the cable you need, right? So you need to know the tension in the cable so you can go to Walmart and get the right strength. All right. Which points should be chosen as pivot points? What are the logical spots to choose for pivot points? Tell me one. The rightmost point. Why is that useful? What could you figure out if you did sum of torques about this point? It would cancel out the tension, which looks nasty. What would you be able to learn about? Which force? We already know the MGs. Would you be able to learn about Rx? Why not? So, but look how easily you could pick off Ry. That's a good choice. Does everybody see that choosing this point eliminates these forces, and then you can just focus on this one? What's another good choice? Somebody else. The leftmost. That eliminates these two, and I can learn about the tension in the string. So that's why sometimes people choose different points when they're doing torque problems. I could choose this one and learn about the tension. That's what I'm going to do. Oh, question?
So since this is like a thin rod, there's no way to learn about RX through torque.
That's not true. You can. You can choose any point you want. Now it would be tricky. What I would do if I wanted to learn about Rx would be, you could choose this point right here. Why is that useful?
Cancel the RY and tension.
Yeah, there'd be no torque here, but now you'd have, it's really freaking hard to do. Oh, but not if you know how to do lever arms. Isn't that cool? So you don't even have to do sum of forces for this problem. If you're clever and see that trick, but most people are not going to see that right away because you're learning. So generally speaking, what do I suggest? Just draw frickin' sum of torques about the obvious pivot point, then write forces in the X, forces in the Y, and answer the exam question and never see me again. And then you'll be happy. I don't know. Let's do it. Let's do sum of torques about this point. Everybody cool with that? I'm going to choose this as the pivot because it's the obvious freaking pivot in the problem. Why not start easy? Now, Rx and Ry cause zero torque because line of action through pivot. Looking good. Let's go. I'm going to get a torque due to the 5 mg. I'm going to get a torque due to the mg. And then I'm going to get a torque due to the tension. All that's got to add up to 0. I'd better pick a direction. How about we say anything going this way is a positive torque. Anything going that way is a negative torque. Unless you have some reason not to do this, just pick the standard math direction. Counterclockwise is positive, clockwise is negative. About this pivot. Let's start working our way across. Can anybody tell me what the torque is for this term, this 5 mg? What's the distance? X. What's the force? And what's the angle? Yeah. So do you agree this is going to be X M, whoops. Five XMG, or whatever you want to rearrange it, positive or negative? Negative. Really sloppy. That's the first term. How about mg? What's the torque for that one? What's the distance? L/2. It's at the center of the rod. Is it going to be positive or negative torque? Negative. What's the torque due to the tension? What's the distance? L. What's the force? T. And then I need the sine of the angle between. Is it 90? Is it theta? Is it 90 minus theta? This is the R vector for T. What's the angle between? From the pivot to here, then I go up to the force. What's the angle between in this special case? Theta. Positive or negative torque? Equals 0. How was that? Okay. Check this out, people. Remember there was another way to get that torque? I could have done R times the force perpendicular. What's the distance? L. What's the perpendicular force? T sine. You agree you get the same result? Wait a minute. But I also have done, oh, yeah, let's leave it. I could do the lever arm, but that's really hard, right? You could be saying, well, couldn't you just say this is the tension force here? And then go from the pivot. And you see how that's going to be kind of tricky? This, you could, in theory, figure out this R perpendicular, and maybe you recognize this is L, this is theta, this is the hypotenuse. So what's this? Looks like L sine theta to me. But that's kind of time consuming, right? In this problem, it's a lot easier to go R, force perpendicular. Am I losing you? Is this okay? Thumbs up, thumbs down, sideways. Where are we at here? Okay, all right. So, moral of the story is there are tricks. Does our R F sine theta work every time? Yes. Is this one a little bit cleaner? Sure. But is this one going to work? Yeah, if it gets the job done, get you out of here. That's good. That's the sum of torques. And pretty much every single one of these problems, after we do sum of torques, we're going to write down sum of, what was the other thing we did in the last problem? Sum of forces. Help me out. Let's do sum of forces in the X equals 0. What's one force in the X off this picture? Rx. That's the rights. Rights equal to lefts. What's the other one? T cos. Got it? And then, so that's sum of forces, right? I'm going to put a box around this one. This was an important equation. That was our sum of torques, I think. About the left end. Now let's do sum of forces in the Y equals 0. Somebody else, give me another force in the Y direction. Sine, positive or negative in this case. So that's an up What else we got in the up direction? Give me all the up forces. What's another one, Peter? RY? I agree. Is that the only ups? I think so. And then what are the downs? The MGs?
Yep.
You agree it's just 6 mg down?
Yes.
We got 3 equations. We got 3 things we don't know. Rx, Ry, and tension. Trivial. Okay, so I'm going to rewrite those 3 equations. This one, this one, this one on the other board and get to work doing algebra. Okay. Give me just a sec. Hopefully I don't mistranscribe them. So we had Rx equals T cosine theta. We had Ry plus T sine theta equals 6 mg. And finally, we had negative 5 xmg minus L over 2 mg plus LT sine theta equals 0. Right? At this point, I read the question. It's sort of like, you know, you write down everything you can and then at some point reread. Let's see what the heck we're trying to figure out. Part A, draw an FBD. Good. Part B, why is it okay to use 5 mg when it's really a normal force? We talked about that. As long as the objects are not accelerating, it's okay to do that. We did sum of forces. We did sum of torques. Part D. Now suppose x equals L over 4. Okay, so that's D. Let x be a special value, the length of the rod over 4. This is what I would typically do on an exam question because it makes the math kind of a little bit faster to work out, right? By writing distances as fractions of the entire length, we see that the length is going to drop out. So I get negative 5 over 4 LMG minus L over 2 mg equals negative LT sine theta. Notice I moved things around a little bit. By doing this way, everything's got a minus sign I can cancel. Everything has an L I can cancel. And I can solve for T fairly quickly here. Maybe what I'll do is I'll multiply by a common denominator here. What is this, 7/4 mg? Double check if I screwed that up. 5/4 plus 2/4 should be 7/4 mg, and then I got to divide by sign. I think that's correct. Everybody cool with that? And then how could I get Rx and Ry? I just shove in this crap. So notice, if you take this result and plug it in up here, we get just using sine divided by cosine as tangent. And we're going to get Ry oh man. That's 24/4. 24 minus 7 is what, 17? I'd punch that into a freaking calculator personally, but I'm on the board, so it's easier for me to do fractions. Got it? What do you think? I'm gonna throw in a little icing on the cake here. I'm gonna draw a sketch. This side is Rx. That's 7 mg over 4 tangent theta. This is Ry. I'll get zoomed out a little bit. Okay. In theory, we could punch in some numbers and figure out this side. Do you agree? You agree I could square this one and add it to that one squared? And you know what I'm talking about when we plug in the numbers? What if I wanted to get this angle, phi? How would you get the angle phi drawn in that picture? Got it? And this is pretty typical procedure. All right. I want to show you the tricks now. Okay, that's the standard stuff that you should be able to do. It's not going to make sense right away, but if we do a couple more of these, you'll be there. You'll be there. I want to show you some cool tricks now. Notice how we get sine theta and tangent theta appearing in some of these equations? And we said at the beginning we could figure it out. I want to show you a new style, okay? I do not want to figure out the angle. I want to figure out sine and cosine and tangent of the angle. In particular, here's my triangle. This was theta. This side was what, 56? What was the height? 42? Is that right? Now, in this case, let's get the hypotenuse really quick. What is that? Should be 56 squared plus 42 squared square root, right? So the square root of 56 squared plus 42 squared. I got 70. Is that what you got? Anybody else? Okay, just Pythagorean theorem. Now, what is sine of theta in the picture? What over what? 42 over 70, the units drop out, punch it in. Don't do sine inverse, just get the sine of the angle. 42 divided by 70, I got 0.6. This is a 3, 4, 5 right triangle. Do you see it? All right. In this case, anytime I need cosine theta, that's going to be 56 over 70. Well, that's going to be 0.8. Double check, see if I'm wrong. Okay. And now, what's tangent of theta? 42 over 56. What is that? 3/4, 0.75 or not? Did I screw it up? 42 to 56, 0.75. Now, I know you're used to just finding the angle, but in practice, when you're doing this chapter, you get sine, cosine, and tangent of the angle rather than finding the angle. That's a trick. It's a shortcut. It saves time. Do you need to do it? No. Could you figure out the angle and then plug it in and keep extra sig figs to avoid intermediate rounding? Yes. So far, so good. And we're not going to check all these numbers, but I want to at least check the tension. So remember, we have numbers for these. Let's plug it in. M was 0.200, and we just figured out sine of theta right here. Help me. Punch in those numbers and tell me what you get for the tension. I'll do it too. 7 times 0.2 times 9.8 divided by 4 divided by 0.6. I got 5.7-ish. Why would I not round this to 3 sig figs? Any ideas? Usually we go to 3. Why would I only go to 2 in this one? How many sig figs did I give on the dimensions of this board? 2. And who built this? Someone at this college, probably me or Angus. There's going to be a lot of slop in here. There's no way we're precise to 1% when we built this thing. You know what I'm saying? So let's look at it. Come on. No, this M, keep in mind, so let me go back out. Right, remember this equation here, there was the 5 mg and this was the mg. This M was the 200 gram. The fact that this was a 1 kilogram was 5 times the, so the M that I had to plug into the formula should be the 200. Are you okay with that? All right, and so here it is. There it is right there. I need somebody to just walk up here and read the scale. Can you do that, please, somebody? Doing great. Yeah. So hopefully it's a little bit, it's somewhere between 5 and 6. What do you read?
Yeah, it's like just a little above 5.
Just a little above 5. Okay, that sounds good. Let's give him a round for reading the scale. There you go, there you go. Thanks, Ryan. Now, in this case, I hope you agree. Look at how much slop is in here. There's like a centimeter right here of slop. This string isn't all the way at the end. When you start adding up the small inconsistencies here, that's what I'm saying why I didn't bother going to 3 sig figs, right? There's a lot of slop in here. Okay. But yeah, if you can see that, you can kind of see that on Zoom, just for reference. This is 0, 2, 4, 6. So it's somewhere between 4 and 6 right there. And that's exactly what we expected. All right. Pretty good for the quality of construction that we chose to use. All right. Questions on that? Should we take a break? Come back and do some more? Sound good? Yeah. Statics. Okay, let's go. Take a break. I've got the time is 5:43. Let's get back into it here. Oops, let's get into it. Let me get on the right board here. All right, so I want to just keep slamming through as many problems as we can to reduce the amount of work you have to do at home. And then I think I forgot a couple of points here. Block here, we're looking at 12.3, and I was just pre-drawing the figures because there's a lot of them. So there's case A, case B, case C, and case D. In each case, it's a massless rod. So the mass of the rod is equal to 0. Each time this block has some weight, W, it's the same block. So in each of these pictures, there's a block with some weight W. You could call it mg if you are opposed to using W. For each rod, basically there's going to be a weight, a tension, and some reaction forces at the pivot. Okay? And then in each case, something is connected at the end and something is connected at the middle. Okay? So basically all of your distances are either going to be L or L over 2. Maybe I'll write that. All right. And I want to start by getting a conceptual feeling for this. This problem is about getting a feel for these problems rather than trying to do math all the time. And we have to do some math, but hopefully we can avoid the worst of it. So if you saw these different situations, right, and there's this beam here in each case, again, the mass of the rod itself is negligible. So the rod, we can assume, is 0 mass, 0 weight from the rod itself. Which one of these do you think would have, or is there one of these that stands out as having a very large tension or a very small tension? In your opinion? Maybe it's not the biggest, maybe it's not the smallest, but is there one that stands out in your mind as having a large tension or a small tension? Either one.
B has a large tension.
You say B has a large tension. And why do you say that? What's your intuition? I agree with you.
The weight is sitting further to the right. And
The weight is really far away from the pivot.
yes.
It has a large lever arm. So for this small amount of weight, there should be a large torque. Excellent. That means you need more force in this cable to balance that torque. Let's write out the equation for it. In particular, right, this would be length times W would be the down torque, right? The downwards torque. What would the upwards torque be? What's the distance? L over 2, because it's either going to be L or L over 2. Remember, the distances are always going to be L or L over 2 in this problem. Sorry about that. What's the force? What's a good name for a force from a cable? Tension. What's the angle I should use? Sine of 30. I tried to trick you. Do you see that? The angle is 30 degrees, not 60. Because not 30 squared. Does anybody happen to know sine of 30 degrees? Oh,
Square root of 3 over 2.
no, that's
1/2.
cosine. Yeah, that's a half. So out of all this, you agree the tension is 4 times the weight. That's the biggest one, I think. Good job. Which tension do you think might be the next biggest? Somebody else. Peter took his shot. Based off that reasoning, which other one do you think might have a large tension in the string? C. Do you agree it's almost the same problem, only now what's the angle? 90. So do you agree we get L times the weight equals L over 2 T sine of 90 degrees? Well, that's just T equals 2 times the weight. That's also pretty big. I'm just going to go out on a limb here. These are not necessarily the smartest ways to support this beam and weight. The tension in the cable has to be more than the weight itself. Okay, so now there's two left, A and D. Which one do you think has the least amount of tension? Which one has the least amount of tension? A or D? Take a guess. What's that? Let's find out. Okay, so what's I have L over 2 to the weight has to equal L T sine of what? Yeah, did I hear you say 30 back there? Well, in this case, you agree the sine 30 cancels the half, the L's cancel. In this one, the tension is equal to the weight. Let's check the other one. What do you think? This one's a little bit smaller. Here's what I want you to get out of this problem. This is what I want you to get. There's two main factors for a given force which will amplify or diminish its torque. The farther it is, the more torque that force causes in general. The more perpendicular it is, the more torque caused by it. So notice in this case, for example, because the string is perpendicular to the beam, we can use a small force and still balance the weight. If it's angled, the tension needs to be a little bit bigger. Got it? So if you have a large distance from the pivot and you're very perpendicular, you get a large torque for a small force. So far, so good? All right. Now, and notice the exact opposite is happening here. When you put this small weight really far away, you need even more force in the cable to balance it because this small weight causes a huge torque way out here at the end. So that's why we need more tension in these two cables. This one requires the most because it's got a small distance and the angle is far from 90. That's why we need a lot of tension there. Cool? Let's go through the reaction forces at the pivot. In this problem, what direction do you think the reaction forces are? To the right and up. Okay. What about this one? What way is the string pulling on this beam? So where do you think the reaction force points? To the left. And do you think it goes up or down? The tension is 4 times the weight. It wouldn't surprise me at all if this reaction force points downwards. Whoops, that's supposed to be an Rx and this is an Ry, right? Because what is 4W cosine 60? That would be 2W up, right? So I think this is actually equal to, you have the weight pulling down here, you have the same weight here, and this, right, this is pulling up. This is a really dumb way to do this problem. But yeah, isn't that interesting? Sometimes the reaction forces can actually hold the thing down to keep it from being lifted off the. All right, whatever. Similarly here, take this one's probably a little bit easier to see. What's Rx for this problem? How much is their force left or right at the pivot right here? How many forces do you see left or right everywhere else? None. So what's Rx? Oops. Now, maybe this helps you see this. Do you agree there's weight down here? The tension is 2 times the weight. So do you agree the pivot has to hold it down? That's probably a little bit easier to see than this first one, right? Now look at the difference in this problem. The tension, this is the weight, the tension is up, but it's only about half the weight. So notice this one has to support the other half the weight. Is this making any sense at all? I did all these pictures in there and I went into the gory detail. I love to slip one of these types of questions somewhere in there on the final, you know, just to see if you can remember this crap. Let's put a star next to this one and make sure you study it, will you? Especially before the final, okay? I don't know how else to tell you other than just make sure you know that shit, okay? Wouldn't it be cool to write a computer code that would draw this and then you could just pick the location of the mass and it would generate it for you? Oh wait, that's the makeup lab. Or it's also question 12.1.5. Believe it or not, it's much easier than some of this other crap that we've been doing. So if you're scared of coding, maybe that one will, I don't know, maybe that'll be easier for you. All right. Now, I have a demo that I like to show that relates to this. I don't know. I should pause. Any questions about anything? Okay, let's go take. Oh, go ahead.
12.1.5 is for coding.
Yeah, you could do that. I walk you through that sets you up how to do a coding problem. And if you get to the makeup lab, it's going to reference that problem, and it'll give you a starter code where I drew most of the crap for you, so you don't have to draw the rod and the pivot and all that crap.
Who will get to do the makeup?
Anybody that wants to. Yeah, so let's worry about that later. Is that cool?
Okay.
Yeah. Sorry about that. Good question. Others? Okay. Now this is a weird one. Give me a second here. Got this weird thing over here. Hopefully, if we're seeing this, is that in the frame or am I watching the camera? Push it forward, right? They want to come over and take a look. Is that better?
Yeah.
Chairs need to go?
Yeah.
It's gonna seem a little bit silly. This device right here is supposed to be a model of the following. That's it. When you bend over, there's muscles in your back. That's this cable. This is what problem is this? Erector spinae. I think it's the top of the next page. What is it? 12.4. It's 12.4. So now I want you to kind of, if you want to actually do the math on it, I wrote all the numbers here, but I want to think about this conceptually. Okay, maybe you've heard about this. When you bend over to pick something up, what are you supposed to do when you bend over and pick up something heavy? Bend at the knees. Why? What if you didn't bend at the knees like this? Now, obviously, the muscles in your back are not a steel cable at 12 degrees, but they can be approximated by that. Now, if you want to come over and feel this, I want you to see that this is not outrageously heavy. Just please, somebody come, just lift this like this and say, oh, that's not too heavy. It's a little heavy, but it's not outrageous. Agreed? Yeah. Okay, now I want you to pick up one of these. Do you agree that feels like it's about 5 pounds? Yes. It is. I put it on the scale. What, we could even throw it up. Is that about 5? Yes. Okay, all right, so go ahead and put that down. So my claim is, let's see how much weight or how much tension needs to be in this cable to support not that much weight over here. Now think about this. I've got a small weight, but what's true about the distance from the pivot? Big or small compared to this cable attaching right here? Yeah, so, right, the cable attaches close to the pivot right here. This is far from the pivot. What about the angle? What do you notice about this angle right here versus this angle right here? This one's close to 90 degrees, very perpendicular. Not very perpendicular, right? So that means I'm going to need a ton of force in this cable to get this to balance. Want to help me just throw some weight on here? Each one of these is 5 pounds. Let's show them in there where. Hard to lift it. Do about 2 more, just stack them. That's about right. Okay, go ahead. So there's a little bit of friction in here, but I can kind of move this around a little bit. In my opinion, I think this demonstrates how crazy it is if you don't bend at the knees. Look at this. The small amount of weight represented by your torso and your body, your upper body here, will cause this huge tension in your lower back if you don't bend at the knees. This is about 17, maybe 19 if I screwed up the count. But basically, I did the math earlier today. The multiplier between the distance and the angle actually multiplies the force by about a factor of 10. And so if you just try to bend over and right, think about this with me. We measured me earlier. My upper body was what, about 100 pounds? That's crazy. Multiply that by 10. No wonder people throw their back out all the time. To be fair, this is only an approximation. It's not perfect. But anyways, I thought you might find that interesting, why you should bend at the knees when you pick something up. It's all about torque. Good enough?
So how much does that mean?
Oh, I've got all the numbers in the problem. You want to take a look at 12.4 real quick? I'm not going to do this, but let's look at it. So the model that we built is actually a model of a child. So when I look at that problem, yeah, so all the information is there. I stole this demo from Harvard. I don't know if you care, but that was pretty funny. I thought they did a good job with it. So if you want to, you could look at what their demo is by doing a web search for Erector Spinae, Harvard. And it's pretty complicated in reality, but this gives you a good feeling for why you're supposed to bend at the knees. And there's the numbers. Does that satisfy your curiosity, Peter? So if you want, you can read all about that. And if you're into biology, that's got some biology in it. So that's cool. And I'm not a biology expert, so I'm going to shut up about that and move on. Good enough for that? Just supposed to give you a conceptual understanding of why you bend. Okay. Now, I want to do this one. We got this ladder here. Check this out. We're going to do problem 12.5 next. A slightly different problem. You might be getting tired, but remember, we've only got a little bit to go, so maybe like 2 more problems. And then we'll talk about the summary today. So just hang in there. Now, my claim is we could set this ladder here. This is not on the verge of slipping. Whereas if I put it like this, there it is on the verge of slipping. So we could start with this problem not being on the verge of slipping and just kind of analyze the forces on it. Now in this one, do you agree there's no pivot screaming out at you? We don't see a hinge somewhere. So what we oftentimes are going to do is we could just view the bottom as a pivot, even though there's not an actual pivot there. So somebody tell me one force that's acting on this ladder right now. What's one force? mg. If you had to guess, where's that going to act? At the, there we go, yeah. So it's going to be an mg down right there. What's another force acting on it? Normal force at the bottom, directed which way? Up. What's another one? Normal force from the wall. Which way is that going to be directed? Anything else? Friction. We know there's friction down here. Which way does it point? Towards the wall or away from the wall? Towards the wall to keep the ladder from slipping away, right? The ladder's wanting to slip that way. You can see it almost slipping there. What about here? Which way is the ladder tending to slip here at the wall? Down. So if there was friction here, which way would that point? Okay. Now I believe in this problem we are going to ignore this friction at the top, but let's draw it and then understand if it's zero by reading the problem statement. Okay, so that's 12.5. Let's look at it now and draw it up. .5 at the bottom of page 102. We got a ladder. Remember, draw those pictures bigger than you think, okay? Lots of big pictures. This problem, they say there's an angle theta right here. Gonna put a little light shading in there. Red. Huh. Red marker, but I must have, oh, there it is. Okay. Remind me, what were the forces? Give me one of them again. mg, right at the center, right? You may want to label it precisely the locations I do. Okay, there's mg. We said there was what? Normal force at the bottom. I'll call that normal force. How about 1? And we said that there's going to be some friction here. I'll call that friction 1. Furthermore, we said that there was going to be a normal force from the wall. Let's call that N2. Geez, I hope I'm using the same notation as I did in the solutions. And we said there might be some friction upwards. Friction 2. This particular problem says negligible friction between wall and ladder. Negligible friction between wall and the ladder. That green marker's dying. I need to get another color. Just underline it in the problem statement. Negligible friction. So do you agree that allows us to get rid of this one? Negligible friction, that term is 0. Now in our previous problems, we always had Rx and Ry. Rx and Ry. Do you see how N1 and F1 kind of look like Rx and Ry in this problem? So when we don't have a physical pivot, sometimes you have a normal force and a friction acting as Rx and Ry. All right. When you have this problem, we're trying to follow our procedure. What are some of the things that we've been doing with every problem that we've drawn today? We do the sum of torques and what else? Sum of, let's do that. Which one do you want to do first this time? Forces. Okay, let's do sum of forces. Let's do horizontal. Sum of forces in the x equals 0. Give me one force in the x direction. Positive or negative? I guess let's do rights equal to lefts, right? What's a rightward force? F1. Any other rightward forces? Equals the lefts. What's a leftward force? What was it? N2, I agree. Okay. That's it. Sum of forces in the y equals 0. Well, what's that going to be? Ups equal to downs. What do I get? N1 equals. So in this case, the forces were really easy to write down. Nice. Ups equal to downs. All right. Now let's do sum of torques. What's the optimum choice of a pivot point in your opinion? I don't know if it helps. Maybe we should write down some common things that we know. What are the knowns in this problem? What are our givens? That might help us to choose this. Do we know the length? Does it say the length? Yes. We know M, the ladder, and we know theta. The ladder's length. And usually we know G. If these are our givens, what things are unknown? Friction, normal 1 and normal 2. G, we have 2 equations. We have 3 unknowns. I need a third equation. How could I get that third equation? Sum of torques. What is going to be the easiest torque equation to write down? If I do the top, the bottom, or the middle as the pivot, which pivot point? Yeah, why would I choose the bottom as my pivot? What benefit does that serve? How many forces are eliminated? 2. If I choose the middle, only 1. If I choose the top, only 1. So by choosing this pivot, you eliminate 2 forces. It's less work, less likely to screw up. Are the others valid? You bet. Okay. All right, so now in this case, let's do sum of torques about that pivot. Now you'll notice, technically speaking, this is not a free body diagram, is it? There's more than one body shown. There's the floor and the wall. But by drawing this picture really big, I argue we could see it well enough probably to get the job done in this case. That said, I want you to get in that habit of kind of drawing these things separate. So I'm going to redraw it too. That way it's a pure free body diagram. Plus, when the engineering instructor walks in, you got to do that. Now, there's going to be a reason for this in a minute. You'll see why we're doing it, actually. Okay? You just have to trust me. There's a reason for redrawing this picture. Okay? In this problem, I need to do sum of torques. Here's my pivot. We know that the torque from N1 is equal to 0, and the torque from F1 is equal to 0. Why is that true? What's the sentence I told you to say? Line of action through pivot. No torque. You could say they're at the pivot and there's no torque, and that is also true. But in general, I want you to get used to this phrasing. I think it's slightly more precise and more general. Better way to say things, okay? I need the torque due to mg. And I need the torque due to N2. Agreed? Those are the only two left. I probably am gonna need a direction. Positive and negative. Which way do you want to call positive? How about counterclockwise, the standard math way, unless we have a good reason to do otherwise? We'll say that's a positive torque. We'll say that's a negative torque, right? Just like before. All right. I want to try and do this one a new way. The torque due to mg, is it going to be positive or negative? Negative. So I'm going to write R perpendicular for mg times mg, and then I'm going to throw in the minus sign. I'm going to explain what this is in a minute. We haven't done it this way yet, right? And then for N2, is it going to be positive or negative? Is N2 going to cause a positive or a negative torque? Okay. Whoops. I'm going to need R perpendicular for N2 times N2, and it's positive, and then all that equals 0. Now you might be saying, why is he doing this to me? Well, I feel like you need to know this, and maybe I'm wrong. And if I'm wrong, I apologize. R perpendicular is actually fairly straightforward for this picture, and I feel like it may help you reduce mistakes. Now, in this picture, I need this distance. I'm just going to keep doodling. Do you guys agree that that is the perpendicular distance? That distance right there is R perpendicular for mg. It's perpendicular to the line of action for mg. What is that? Any guesses? It's not half the length. Do you agree? Absolutely. This side is L over 2. Do you agree? That is L over 2. We've got a cosine. This theta is turning invisible here. There was a theta right here at some point. Do you agree that this side is going to be L over 2 cos? Cool. And so, now to be fair, whoops, what's this angle up here? It's not theta. What is this angle right here that I'm trying to, what would this angle be?
90 minutes.
Right? It turns out sine of 90 minus theta is cosine of theta. So it would have worked out the other way. More on that in a minute. Okay. I know what this is going to be now. How do I figure out R perpendicular for N2? Let's walk through the steps. I want to get a lever arm or an R perp for N2. What's one step? What was one step I did for MG? What's that? Line of action. There's the line of action. Then what? Draw the I need a line that's perpendicular to that. We call that drawing the perpendicular bisector. You agree that this is a perpendicular bisector? So this is R perpendicular for N2. Following along there? I hope you agree drawing the separate free body diagram was handy, right? It's a mess trying to deal with this. That's what I was trying to say earlier. If you don't draw a separate FBD, at some point the problem's going to catch up to you and you can't read anything you wrote anymore. And look, this is already crazy clogged. If we didn't draw this big, you would have lots of trouble. Help me out now. What is R perpendicular for N2? What is this side of the triangle? What sign? This should be L sine theta. Outstanding. Good job. Because if this is theta, that is theta. This side's L, we got it. So notice I could plug this crap in, negative L over 2 mg cosine theta plus L sine theta equals 0. Woo! What drops out? L. Moving some stuff around. What do we get here? I guess we get mg over 2 cosine theta has to equal n2 sine theta. Just moving this side over to here, then flipping the sides. The L's drop out. At this point, we have written the force equations. We have written the torque equation. The logical thing to do is read the question and see what we're supposed to do. You know what I mean? Because at some point we forget it. Draw an FBD, write some forces. Determine the frictional force at the base of the ladder. Determine the frictional force. It's not at slipping for part C. So in part C, I'll get out of the way. We're supposed to get F1. Well, how would you do that? Maybe if I label this, it's easier to communicate. This is our sum of torques equation about the bottom. We've got a force equation in the Y, and we've got a force equation in the X, right? I'm looking for F1. Describe how you would get it.
Solve the torque equation for N2. Like that. And for N2.
And that's F1. Yes, something like that. You agree? So in this case, basically, if we solve for N2, do you agree we get that? Look at the picture, right? This has to equal that. So if we can get this, we got that. So in this case, N2 equals F1 equals, is that going to be mg over 2 cotangent theta? No, I think it's mg over 2 tangent theta, right? What is it? Sine theta, it would be mg over 2 times cotangent theta. Let me check the Zoom board. Okay. Or you could figure it out this way. That's probably a little prettier. Sweet. Notice we did not use mu n. Do you agree? It's not on the verge of slipping. Don't use mu n. Part D, however, what does part D say? I want the min coefficient to keep from slipping. I want the minimum coefficient, then what could I do?
Substitute F with N static.
And I would use which normal force?
Normal force 1,
Outstanding.
which is mg.
And do you agree the mg's drop out? When you plug that in, the mg drops out. We would get mu static equals what? The mg's drop out, it's cotangent theta over 2. Kind of looks like a weird set of alien symbols if you. Yeah. After a long day, some of these symbols just start to look crazy, don't they? All right. So far, so good. This is all written up in the solution. You got it already here, but if you like that one, take it by all means. Yeah. Sometimes I write it a little different on the board, right? So better safe than sorry. I have a fun question for you now. Unless you have any questions for me before we. Okay. Oops, wrong one. That's 8. Come on. There we go. Okay. Screensaver auto turns on every 5 minutes. Come on. Sometimes this job drives me a little crazy. All right. Okay. I want to go through a scenario with you. That's pretty close to on the verge of flipping. Do you agree? When I put it right about there, do you agree? It's like, oh my gosh, it's like really close to slipping. Agreed? Okay. Come on, stop slipping. Oh my gosh. Okay, it's right on the verge. Okay, so now I'm going to take this mass and I'm going to hang it on here on one of these low rungs, probably the second rung so it can hang. So I want you to think of this as like a person climbing up the ladder. Do you agree it's very close to slipping right now? My question is this. When I hang this mass here on the second rung, close to the bottom, is it going to slip or not? What do you think? Okay, I hear a no. A lot of kind of, okay, good enough. Let's take a look. I'm going to be rough with it here. You agree it's actually pretty stable when you add that mass to the bottom, right? Okay, if I do this even more gently, right? If I hang this on there, it's actually more stable with this mass down low. As you climb the ladder, what's going to happen? Anything or nothing? Oops. Where did it start to slide? What's that? About halfway. So an interesting thing can happen here, and you could actually use these diagrams to help understand it. Let's maybe look at it. Now imagine we have this exact same problem. Whatever. And I add another mg here, right? Let's say I add a second mg. Well, what's that going to do to this problem? And in fact, you can start thinking about not just the forces, but also the torques. And if you apply this mg down low versus up high, what's going to happen to it? And so in this case, maybe you would want to do a sum of torques about this pivot point. And if you want to learn more about this problem, I guess you could do it. It's problem 12.6. You could do that one at home. But I just kind of wanted to foreshadow this one and let you guys pick that one up at home and just see if you could handle this with an extra force term in there. Got it? All right, but I don't know. I guess if we wanted to, you could think about this lever arm, right? Once you cross over the center point, the lever arm for this term gets very large. As a result, what is that going to do here in this torque equation? That's going to make N2 bigger, right? Because it's going to have to balance more term here. And then if N2 gets bigger, you need more friction. You need more friction. Your coefficient either has to go up or the thing is going to slide because you don't have enough. Is that good enough on that? All right. We'll do more of this next time. But before we leave, let's review. Remember I said we'd review the sheet on page 99 real quick? So let's kind of go through this and see if this checklist is starting to make some sense. Let's just read together, okay? When you're doing a static equilibrium problem, the object is not rotating and it's not translating. The sum of forces and the sum of torques are zero about any point. What is the first thing we do? Draw a picture and just try to get a feeling for it. You could draw some forces, and then sometimes you draw a separate sketch showing only the lengths and the angles. Don't forget the reaction forces at the pivot. Sometimes people forget those. Just draw an Rx and Ry if you got a pivot point. I like to do sum of torques first. Other people want to do forces first. They're both great strategies. Just do something, and usually the only way to solve your way through this test question is to do both. So you're going to have to do at least one sum of torque equation and probably at least one force equation. And you could do 2 torques and 1 force, or you could do 1 torque and 2 forces. But when you do the torques, pick a pivot point, cancel out any forces which have line of action through pivot. Then you can draw a positive direction and a negative direction and get the torques using RF sine theta or R perpendicular F or RF perpendicular. Okay, keep track of all the minus signs. And then I like to do I do torques first and then I do forces second. Sometimes I'll redraw the force problem. We'll do that next time. Bullet 4. At that point, usually you have 3 equations, 1 for torques, a couple for the forces. List them neatly, reread the problem, solve for something. Okay, check your answers. More on that next time. That's kind of what we did today. Are you able to follow that a little bit? Let's pick up there next time. Oh my gosh. 4 minutes early. What's wrong with me? There must be an alien in here. Something's wrong with me. Oh.